Students. In this lab, welcome to lab 2. In this lab, we will study about linearity and time invariance of systems. Basically, what we'll do, we have some systems, like we have 4 systems. We will try to determine the linearity and time invariance properties of the systems. Lab 2 report submission need to include both theoretical proof of linearity and time invariance, plus your MATLAB simulation codes, results, including figures and discussions for the 4 systems. To do this lab, we will use a function called lab2 systems. So basically what this function does is you will give an input signal x of t, then you have the system, it has the system, the function has the system, and then at the output you will get the output of the system. So first of all, what you will do is you will try to determine the linearity and time invariance mathematically. Okay. For example, here the first system, I try to formulate the mathematical expression for the first system. The first system is y of t is equal to x of t times u of t, where u of t is the unit step signal, as you know. So we will determine the linearity and time invariance mathematically. For example, we will do it as below. Let's say y of t is equal to x of t times u of t. Then if you remember in the theoretical lecture class how we prove linearity, if the input x1t pass through the system, now in this case is system 1, we have the output y1t, what is just we see the mathematical expression when we give x of t to the system. At the output, we have y of t is equal to x of t times the unit step function u of t. So it means all the signal, part of the signal before 0 will be 0 because of the unit step function. So if I give x1t, then the output will be y1t is equal to x1t times ut. If I give the input x2t, then y2 of t is equal to x2t times ut. Now let's create another input signal, which is a linear combination of x1t and x2t, which is equal to ax1t plus bx2t. So if I give x3t, what will happen to the output? Of course, from the mathematical relation here, y3 of t will be equal to x3 of t times ut. So we substitute x3 of t. What is x3 of t? ax1t plus bx2t, and everything multiplied by ut. So if we rearrange this means ax1t times ut plus bx2t times ut. x1t times ut is y1t. x2t times ut is y2t, which means y3 of t ay1t plus by2t, which is actually it satisfies the linearity property. So we proved the system is linear. Let's try to prove whether this system is time invariant or it is time variant. Okay. If again from the theory class, from the lecture class, if we have x of t and pass through the system, system 1 in this case, y of t is equal to x of t times ut. If I have a delayed input, if we delay the input, xt minus t naught, then the output should be delayed by the same amount. So yt minus t naught is equal to x of t minus t naught, ut minus t naught. So we should get this. So in other words, if I give a delayed input to the system, I should get this one. Okay, that means when I pass the signal through the system x of t, then I get yt. Then I delay the output yt. Then if I give an input xt minus t naught, and if I delay the input first, I should get the same output, that means. So let x1t is equal to xt minus t naught. So in this case, what did I do? I just delayed the input first, okay? So when I delay the input first and then pass it through the system after that. So what is y1t? Y1t is x1t times ut. What is x1t? X1t is the delayed input. So we substitute the delayed input. So this means y1t is x of t minus t naught times ut. So in this second case, the input is first delayed and we pass it through the system. In the first case, first we pass the input to the system and then we delay the output, which is this one. So if we compare this and this, are these two the same? No, they are not the same, because here I have ut, here I have ut minus t naught. So that means yt minus t naught, the output, the delayed output, is not the same as y1t, which means the system is not time invariant, or in other words, the system is time variant. Okay, now this is the way you do mathematically. So for all the systems, for 2, 3, 4, you'll go to the MATLAB function lab2 systems, and first you'll identify the type of the system by writing the mathematical expression for the output yt for system 2, for system 3, and for system 4. Then by following these steps, you will prove whether each system is linear or time invariant, linear, time invariant, and you will complete this table. In the theoretical analysis, we have to see the proof for each system, like I did here for system 1. You have to do for system 2, 3, and 4. Now let's try to prove this using a MATLAB simulation. Okay. Now again, I will try to show this process for system 1, and you will do for system 2, 3, and 4. So for system 1, how we prove linearity and time invariance mathematically in MATLAB. Okay. So here, for example, I create a time signal, a time vector from -2 to 10, and the time step 0.05. And I create two inputs, x1 and x2, is equal to, what is x1? x1 is equal to t greater than or equal to 0 and t less than 1. This is actually a logical expression. So that means if I give this time vector, then the input x1 will be 1 between 0 and 1. Okay? Otherwise it will be 0, because this is logic, this is end, t greater than 0 and t less than 1. If I give x2 is equal to t greater than or equal to -1 and less than 5, then x2 will be 1 between -1 and 5. Otherwise it will be 0. Then I pass x1 through system 1. This is a function, lab2 systems. I pass it through this and I will get y1, and I pass x2 and I will get y2. Then I get y12, y1 plus y2. Then I will create x3, which is x1 plus x2. Then I pass y3, okay, through the system. And if I have y12 is equal to y3, then we call the system is linear. Okay, let's go to MATLAB and let's see this process. Okay, first of all, let me explain what lab2 systems. This is a function. Okay, this function, what does it do? Okay, first of all, this is a function because it's defined by function, and I have an output y, and The name of the function is lab2systems. As you see, the file name is lab2systems. And it will have an input time t and x. Okay, we have to input the time vector and x, the input signal, and we have to input the system number. The system number should be 1, 2, 3, or 4. Okay. Then after that, I have this one. It will check which system number you put here. If system number is 1, then this is the expression for the output y. So y is equal to x times t greater than or equal to 0. T greater than or equal to 0 means u of t, because it will be 1 for t greater than or equal to 0. So that means this is x of t times u of t, which I did it before. Okay, so I did this example already. And else, if it is system 2, you have this expression and you have to find the mathematical expression for this. Else, if you put the system number 3, so it will check here in the system number. If you put the system number 3, then the output y is this. That means this is the system output. If it is system number 4, the output is y is equal to this one. So you write the mathematical expression. Otherwise, if you put another system number, for example, if you put 5, it will say it is an error, because system number should be 1, 2, 3, or 4. Okay, this is what it does. So for basically what it does is it will see the system output for each system number. Based on your selection of system number, you will have the system output, or in other words, it means you defined the type of system. Now let's check again for system 1, which is, as I said, system 1 is x of t times u of t, which is this one. Let's check linearity. Okay, the linearity proof. Okay, let's see the MATLAB script file. I just made a small script file, and I call this the name of the file lab2v1. Just it's a name. You can give it any other name you like. And usually I start with clear all. Clear all means clear all variables in the workspace. Remember, this is the workspace, and so that to avoid any confusion with the variables. That's why I clear all. Now t we define from -2 to 10, and x1 is t greater than or equal to 0 and t less than 1. Okay, actually let me show you what this logical expression means. For example, if I say t is equal to between -5, okay, and 1 and 10. So it is between -5 and 10. Time step is 1. That means it is -5, -4, -3, negative until 10. And if I define x is a vector. Now x is equal to t greater than or equal to 0, t greater than or equal to 0, and t less than 5. Okay, which means it is between 0 and 5, including 0, excluding 5. See what happened now? It will check with t vector. So x will be 1 if t is equal to 0, or and t is less than 5. So here t is -5, x is 0. T is -4, x is 0. T is -3, x is 0. T is -2, x is 0. T is -1, x is 0. And t is 0, x is 1. T is 1, x is 1. T is 2, x is 1. T is 3, x is 1. T is 4, x is 1. T is 5, x is 0. And for the others, it is 0. So x will be 1 for t greater than or equal to 0 and t less than 5. It is a logical end. This is logical end. So it will compare with t, and it will determine whether x is logically 1, 0. That's what it does. So here, from this time vector definition, x1 will be 1 between 0 and 1, and x2 will be 1 for t greater than or equal to -1 and 5. So x2 will be 1 between -1 and 5. That means, okay. So if I plot it, I can show you by plotting this. For example, let me clear this window first. Clear CLC. Remember, t is between -2 and 10. x1 will be 1 between 0 and 1. x2 will be 1 between -1 and 5. Let me take this directly from this one. I copy it and take it to the MATLAB command window, paste. Okay. Now let's plot x1. Plot t versus x1, and let me make it, this is black color. Okay. Hold on top of it I will plot, hold on, and let me plot x2. Plot x2 with red color I select. Okay, remember, from this x1 will be 1 between 0 and 1, x2 will be 1 between -1 and 5. Okay, let's see the graph now. You see the graph, x1, which is black color, it is 1 between 0 and 1. This is the black color. You see the black color, it is 1 between 0 and 1. Otherwise it is 0, completely 0 for the rest of the time. That means, and x2 will be 1 between -1 and 5 and 0 otherwise. x2 is, this is between -1, this point is -1. The red color is x2 between -2 and here 5, between -2 and 5. Otherwise it will be 0. Okay, otherwise it will be 0. So that means I defined two input signals. Then I create x3, x1 plus x2, the addition of the two. Okay, and for example here, again I define, this is x3. I will show you x3 is x3, x1 plus x2. x3 is equal to x1 plus x2 again. And again, let me plot, hold on, I will make on top of it, plot x3 with another color, let's say blue color. Okay, let's see the plot. So x3, remember, is x1 plus x2. So this is the output of x3. x3 is like this kind of curve. It's actually I did it on the same graph. So this is x3. Okay, this is x3. It is between, again, between -1 and 5. Okay, this is how we plot each individual inputs. Okay, so that's how it is. Now we pass x1 into the system. So we call the system function, this function, remember this function, we call this, and the input is time vector x1 and the system number is 1. And then we pass x2 again through the same function and we get y2. And we determine y12, which is y1 plus y2. Now we pass x3, which is a combination of x1 and x2. And I call this is x3 to the system, and I get y3. Now, according to linearity, if y3 is the same as y12, then we say the system is linear. So to check this, we plot y12 and y3 on the same graph. So here, plot t y12. y12 is y1 plus y2 with black color here, okay? hold on, plot t y3 with red color. So on the same graph I plot and I give axis labels. So let's see the output. That means let's see the result. So it means y12 and y3 should be on top of each other, one with black color, the other with red color. Okay, so let's run this this script file. Okay, what's the name of the script file? lab2v1. lab2v1. Okay, so run it. It's running now. Running. Now we have output here. See, this is the output. You only see one graph, red color. Where is the black? The black color is actually the red becomes on top of the black. That's why we cannot see it. How we can see it is on top? If we insert here legend, for example, legend means labeling each output. You give a label for each output. Then we will see that we have two colors here. It's a little slow here. So the black and the red are on top of each other. Yeah, it comes now. So the black is, I have two datas, one black, one red. So you cannot see the black because it's exactly the same. That means the black is y12 and the red is y13. They are the same. That means. So that means the system is linear. If I delete the red, I can see the black is below. So I can delete the red part, and I can show you that the black is below. So delete. When I delete this, I should get the black behind. Yes, the black is behind here. This is a black, exactly the same. So we proved the system is linear. That means. Okay, now let's prove time invariance. Remember how we prove time invariance? Let's go to refresh time invariance. What we do, we pass the input through the system and we get the output and we delay the output. Okay, we delay the output. This is first case. Second case, we delay first the input and we pass it through the system. Okay, in this case here, mathematically y1t. Then the first case, the output of the first case should be the same as the output of the second case. If this condition is fulfilled, we call the system is time invariant. Otherwise, the system is time invariant. How we do this? Okay, we do it again. Here is the time vector. X1 is between 0 and 1, it is 1. X2, I create another X2, which is 1 between -1. X1 is 1 between 0 and 1. And I create another input X4, which is by shifting X1. Okay, by shifting X1 by how much here? It is 1 between -1.5 and 0.5, -0.5. So I shifted by 1.5 to the left, So I created X4. Then I pass X4, okay, the shifter signal through the system. Okay, here I pass X1 through the system. Okay, I pass the original X1 through the system. Here I pass the shifter signal, which is shifted by 1.5 through the system. That means the output Y4, when I compare it with Y1, should be shifted by 1.5 to the left. Okay, so Y4 is the same as Y1 shifted by 1.5 to the left. Otherwise, if that is not the case, then we say the system is not time invariant. or the system is time variant. Okay, so let's go to the MATLAB again. The MATLAB script file here I created lab2v2. Here is again is the script file. Again, time vector between -2 and 10. X1 is 1 between 0 and 1. X4 is 1 between -1.5 and -0.5. So I shifted X1 by 1.5 to the left. That means if we try to plot and see, we can check this. Let me do that here. Actually, I can copy this part and I can show you that this is the case. My MATLAB is a little slow, so okay, I will take it from this until this. Copy. I will plot x1 and x4, and I will show you plot t x1 with black color. Hold on. On top of it, I will plot t x4 with red color. Okay, and I see both. Okay, together. I should see that x4 is shifted by 1.5. You see, here is the black color is x1. It is 1 between 0 and 1. And the red color is x4. It is shifted. It's between actually -1.5 and -0.5. Exactly, this is between -1.5 and -0.5, which is shifted. That is. So if the input is shifted by this amount, then the output should be shifted by the same amount to be time invariant. Okay, so to check this, so I pass x1 through y1 here, and I pass x4, okay, the shifted input, through and get y4. Then I plot y1 and y4. When I compare y1 and y4, y4 should be shifted by 1.5 compared to y1, so to the left. Okay, so that should be the case. So let me call this script file lab2v2. Script file is lab2v2. Lab2v2. Run it. It's running now. Okay, this is output. As you see here, what is the black color? The black color is y1. y1. The red color, which is everything is 0. The red color, everything is 0. If the system was time invariant, then the red color should be, when I see the red color, it should be the shift of the black color 1.5 to the left. Okay, so that means when the y1 shifted by 1.5 to the left, but I don't see this. I don't see this, so I didn't get this. That means the system is not time invariant, or the system is time variant. Okay, when you do for the other systems, you will see this clearly, how time invariance property can be proved. For this example, because it is not time invariant, you cannot see the shift. But for the others, for some of the other systems, because some of them are time invariant, you will see this. Okay, so that's all about linearity and time invariance example. So what you should do, you will do this exercise for systems 2, 3, and 4. Where you get this system 2, 3, and 4, you will get the systems from lab2 systems function. Okay, as I said. So if the system number is 2, this is the expression. And if system number 3, this is the expression. If system number 4, this is the mathematical expression. So you change it and you write it in a form like x of t and something y of t. So you will complete this table. And you will do mathematical proof for each linearity and time invariance. And you will do MATLAB simulation. And you will make sure that the simulation matches the theoretical calculation. That is actually the idea, to show your mathematical proof is the same as your MATLAB simulation. Okay, that's all about Lab 2. Thank you very much for listening to this lecture.